As a first example from Dynamics, we are going to start with the simplest possible situation. We will have a 4.0 kilogram block that rests on a horizontal frictionless table. A force F with a magnitude of 50 newtons and an angle of 25 degrees with the horizontal begins to act on it, and we will determine its acceleration. This, these questions are always solved based on Newton's laws, and specifically on Newton's second law, which we write in vector notation as the vector for the net force. It must be equal to the mass times the vector for the acceleration. This expression is very elegant and short, but it's really a shorthand for two requirements that actually give us two equations eventually. We always write, when we get to the solution of the problem, we always write this equation for the components. So we're going to have the sum of x components of all the forces has to be equal to the mass times the x component of the acceleration. And the sum of the y components of all the forces has to be equal to the mass times the y component of the acceleration. So let's see what we have. Here's the block sitting here on a horizontal table, and I will draw the first vector for gravity pointing down always towards the center of the earth. Then I have to draw a second vector to account for the normal force. Remember, the normal force is the accounts for the interaction between the block and the table. And then I will have a vector for the force F pointing up and to the right at some angle, well, at an angle of 25 degrees with the horizontal. Because we will apply Newton's second law by components, we need to know the components of each of those three vectors. So I will need to choose a coordinate system, and the most natural choice here will be to pick x to the right along the table and y to be directly up. With that choice of a coordinate system, I see that my gravitational force vector will have components 0 for x and minus mg for y. For the normal force, once again, I will have a 0x component, but I will have a positive y component. I don't know how much it is, so I'm just going to use a symbol and I'm going to call it plus Fn. For the force F, of course, I will have to use two symbols, Fx and Fy. And I don't know them directly, but I can actually figure out what those Fx and Fy components are. For that, the easiest thing is to actually take the vector and draw it on a separate diagram here, keeping the same coordinate system with the same orientation, x, y, x to the right and y up. Here's my vector F. And here's the angle theta, which is actually 25 degrees. So I'm going to draw a perpendicular from the tip of the vector down to the x-axis and see that the adjacent segment here is going to be the x component of the force F, and the opposite, the side that faces the angle theta, will be Fy. Using trigonometry, I know that the side that faces or its opposite the angle is going to be the hypotenuse F times sine of the angle theta, and numerically I can actually see what the y component of the force will be. It turns out to be 21.131 newtons. I'm going to keep extra digits. This is still very early in the beginning of the solution, so I do not want to accumulate any round off errors. For the x, remember that segment is actually adjacent. It's the adjacent side in the right triangle. So from trigonometry, I know that is going to be equal to the hypotenuse of the triangle, the little triangle at the here, F times cosine theta. Numerically, that will be 45.315 newtons. So I know Fx and Fy. Let's mark them here on my diagram here with the rest of the forces. And if I need to know what they are, I will either work with a symbolic expression. For Fy will be F sine theta, and for Fx will be F cosine theta, or I can just use the numeric values. So here, let me highlight them so I know where they are. Now I'm ready to go to Newton's second law, to the two equations that are written for the x and for the y components. Let's start with the x component. I'm going to have here that the sum of all x components has to be equal to the mass times the x component of the acceleration. So I'm going to go around the vectors and add the x components. Gravity will have 0 component for the x, and the normal force will have a 0 for the x component. But the F force, the 50 Newton force, has an x component. So my equation here turns out a very easy, simple one. fx, or f cosine of theta, remember from the lower left corner where we looked at the x and the y components of that force. So f cosine theta will have to be equal to max. Here is where most of the people will stop with the solution of the problem. Because we can plug in the numeric values for the force and the angle and the mass and get the x component, which in the end you will find out that that is the entire acceleration of the block. So if you're solving a problem on your test, this is where you usually stop. I want to go a little bit further to show you some subtleties that usually students miss. Let's look at the y equation. For the y equation, we're going to have sum of all y components has to be equal to the mass times the y component of the acceleration. Now, all three forces here have y components, so I'm going to write minus mg for the gravity, plus Fn for the normal force, and plus Fy for the y component of that force. Now, the Fy, remember, was F sine theta, so my overall equation here will be minus mg plus Fn plus F sine theta has to be equal to may. Together, these two equations could be considered as the equations of motions, the equations that govern the motion of this block. Together, they can give you much more than simply the acceleration of the block. And they are frequently called equations of motions when you go to higher levels of physics. So let's put them here up on top. And this is why I usually look back to the problem to check. A lot of times I get bogged down with the analysis and I even forget what the question was. So if you end up forgetting what the question is, here's where you go back and say, okay, I have my equations of motions. Let's see what the problem asked me to do. And then I see that the question here was about the acceleration. What will be the acceleration of that block? The first equation will give me the x component. So I'm going to have f cosine theta will be equal to max, or numerically here, when I put all the numeric values, I see that the ax, the x component of the acceleration, will be equal to 50 cosine of 25 divided by 4, which gives me 11.33 meters per second squared for the x component of the acceleration. Again, this is where we usually stop and say this is the answer to my problem. But let's see what the y equation gives us. The y equation is minus mg plus fn plus f sine theta is equal to may. At first glance, it seems like we have a problem. We don't know what the normal force is, and we don't know what the y component of the acceleration is. But no worries. It turns out that we can either have a normal force Fn or a y component for the acceleration, but we never can have both. And think about it. The block is sitting on the table. It has two possible scenarios. Either the block remains on the table, sliding left and right, and if it remains on the table, it retains the contact with the table, so we have a normal force. But in that case, it's not going up or down, so it has a 0 y acceleration. The other scenario is if the box should have a y component to its acceleration. That means its vertical motion is changing. The block is either taking off or lifting off the table or falling down through the table, and in that case breaking the table, so there will be no more physical contact between the block and the table. So we can spell out this rule in very simple. Either Fn is going to be 0 or the Ay will be 0. We will never have to worry about both of them sitting there in the equation that we don't know. A reasonable guess here for our problem is to assume that the block remains in contact with the table. In other words, that it has no change in the vertical motion. In other words, it has no y component of the acceleration. And so the equation then becomes equation for the normal force. Minus mg plus fn plus f sine theta has to be equal to 0, which gives me for the normal force to be equal to mg minus f sine theta. And now I can put the numeric values for the mass, the gravitational acceleration, which is 9.8. The force, remember, F was 50 newtons and the angle was 25. So it turns out that the normal force is 18.1 newtons. Now the problem doesn't ask me about that, but a lot of times you'll see in next examples we will need that normal force. So I'm giving you here the most powerful, robust, foolproof procedure that will always allow you to solve any problem from dynamics if you master these steps. Now, if you're curious to say, well, what happens if we guessed wrong? What if we guessed that we had some y component for the acceleration and the block or the block was off the table? So let's see what happens. If you guess that the normal force is 0, and then we have some y component for the acceleration, the equation then is minus mg plus f sine theta has to be equal to may. And then for the y component of the acceleration, you'll find out that it's actually minus 4.52 meters per second squared. Now, if you assume that the block is actually lifting off the table upwards, we would expect a positive acceleration, positive component for the positive vertical component for the acceleration, but yet the equation tells us negative component, so it doesn't make sense. So this is how we know that we have guessed wrong. Now for this problem, it's pretty obvious. The natural choice is pretty easy to spot, but sometimes when the problems get more complicated, we literally have to guess one way or another and check for the answer. If an answer emerges that doesn't make sense, that means it's the wrong answer. So to summarize what we have done in this example, I walked you through the steps that will actually give you the two equations of motion that govern the motion of that block. That is that block. That is the most important part here in these dynamics examples. We also determined that the y component of the acceleration is 0 and that the x component of the acceleration was 11.33 meters per second squared. So with the two components clear, now I can write the final answer in terms of magnitude of the acceleration, which in this case will be 11.33 meters per second squared, and that in a direction. So I can see that the direction of my acceleration will be to the right. And look at that. In the meantime, we also determined that the normal force on that block, even though the problem didn't ask us about that, is equal to 18.1 newtons.